Search for the word car, and a plain keyword system will completely miss every document that says automobile instead. The two words mean the same thing, but the machine has no idea. Latent semantic analysis, introduced by Deerwester and colleagues back in 1990, was an early and influential fix for exactly that gap. It uncovers the hidden meaning behind words. And today we're going to walk through how it works and why it mattered so much. The method has a clean four-step shape. Let's follow a collection of documents through it. Start by building a big table. Rows are words, columns are documents, and each cell holds a count or a weighted score for how often that word shows up. This table is enormous, mostly zeros, and pretty noisy, but it captures who uses which words where. Everything LSA does begins from this one raw picture of the collection. Now comes the mathematical heart. We apply singular value decomposition, a standard way to factor that big table into simpler pieces. Think of it as pulling out the strongest patterns of word and document usage hiding inside all those counts. Rank from the most important pattern down to the faintest one. Then we throw most of it away on purpose. We keep only the top few hundred dimensions and drop the rest. This lower dimensional squeeze is the magic step because it merges related words and filters out the noise, leaving the concepts behind the words instead of the surface spellings. Compression, oddly enough, is what creates the meaning here. Finally, every word and every document becomes a dense vector in a shared concept space. Words that appear in similar contexts land near each other, even if they never once co-occur. So car and automobile end up close, and you measure similarity with a simple cosine. That single move is what turns raw counts into something that behaves like meaning. So step back and compare the two ways of matching text. Plain keyword matching only finds documents that use your exact words. It misses synonyms entirely, and it gets confused by words that carry several meanings. You end up searching the surface of the text, never the meaning underneath, which is exactly why so many relevant results slip right past you without a trace. Latent semantic analysis groups related words and documents by their latent concepts. Because it works in that compressed concept space, a query about cars can surface documents about automobiles that never use your word at all. You're finally matching on meaning rather than on the exact letters someone happened to type, and that opens the door to real semantic search. Let's lock in the three ideas that define LSA. First, it factors that word-by-document table using truncated singular value decomposition. Keeping only the top dimensions is not a shortcut or a memory-saving hack. It's the whole point because that very compression is what forces related terms and documents together in the same region of space. Second, those latent dimensions capture meaning that goes beyond exact words. Words used in similar contexts get similar vectors, so synonyms line up and the many meanings problem softens. The model is effectively reasoning about concepts, not just string matches, which is a genuinely different way of looking at text. And third, this was an early precursor to modern embeddings. Mathematically, it's the same idea as matrix factorization, and it pointed straight at today's dense word vectors and dense retrieval. LSA quietly set the stage for everything that followed, decades before neural embeddings made the approach a household name. All right, let's gather up the essentials so this really sticks. There are 4 things worth taking with you. Latent semantic analysis uncovers hidden meaning by finding latent concepts across a large text collection. It builds a word-by-document table, then applies singular value decomposition and keeps only the top dimensions. That compression maps words and documents into a shared concept space, so synonyms like car and automobile land close together. It was an early precursor to today's embeddings and dense retrieval. Curious about more NLP explained simply? Visit Standarity.com, where these ideas get unpacked one at a time.